Segmentation of large images with complex networks. And the authors are Oscar Quadros Linares, Glenda Michele Botelho, Francisco Rodrigues e João Batista Neto, and is going to be presented by João Batista Neto.
Hi, good morning everyone. Actually this paper should be presented by Glenda, but unfortunately she couldn't make it. The subject here is, it's not a medical application, I'm afraid, but it's segmentation of large images via complex networks. What I'm going to do here is try to convince you why this is a good approach for segmentation. Secondly, I'm going to provide you with some key concepts related to our methodology, and then comes the methodology itself, followed by some experimental results and some conclusions. Okay. Graph-based segmentation is not actually a new thing. Yeah? There are in the literature many techniques which consider modeling an image as in a graph and then provide some segmentation of some sort. Among the techniques I could point out spectral clustering, graph partitioning in general, and algorithms which are designed specifically for detecting communities. And the major problem with those techniques is that they are very time consuming, and in the end of the day they are not very suitable for large images themselves. So the objective of this work is try to make it useful for larger images. And I mean large images, I mean real images, more than 2 or 3, 4 megapixels in average, okay? And specifically we are trying to look at some algorithms which detect communities. And I'm going to say why we've picked up those algorithms. Anyway, communities. By modeling an image as in a graph, yeah, as a graph, or we can consider that every pixel is going to be a node, and the edges will represent somehow relationships between those pixels, okay? And it turns out that it's a quite large problem to be solved by computers because the graph is very large, and then you not only have problems with memory but also with performance. So spectral clustering, for example, when it came out, it wouldn't be suitable for images larger than 100 by 100 pixels. So it wouldn't be feasible for larger images than that, okay? So what we are trying to do is we are going to, instead of considering a single pixel as a node for the complex network, or as a node in the graph, we are going to group a region which by means of superpixels, and this is one of the key concepts in our work. Okay, so what is a superpixel? So then it's a region of pixels, and how do we go about calculating the superpixel? So basically what the technique does is we start with a regular grid, and then by iterating, by an iterative process, we try to adjust these regular grids to the boundary of the image itself, okay? So, and this iterative process stops the number of iterations actually is very much related to the size of the grid cell, nothing more than that. So we came out with that experimentally, basically, and then in fact we can do it very quickly with very few iterations. So what the algorithm does is you always take two neighboring superpixels. So the point is how to move one boundary pixel of the superpixel to one superpixel or to its neighboring superpixel. What you consider here is the equation establishes two terms. The first one here takes in account the gray level or the image content itself. In this case, this is considering a gray level image. All you have to do is take the pixel itself, the gray level itself, and consider the mean value of the superpixel. Remember that we are dealing with a set of pixels. Then you have to have a measure that represents the whole superpixel. So in this case, we took the mean intensity of the superpixel, and the second term relates the centroid, the position of the superpixel itself, or sorry, the pixel, which is the coordinate of the pixel, x and y, with the position of the centroid of each superpixel. So you do that, you compute this estimate for both superpixels, and then you assign the boundary pixel of the superpixel to its neighboring superpixel, or you keep it in the superpixel where it originally comes from. So what you end up with is, with a region which fits the boundary of the object quite nicely. That's what it does. So, as expected, what we do next, I'm sorry, here, okay. What another key concept is, how do we compute the graph? Basically what we have to do is have to provide some means of establishing the weights of the edges of the graph, and you can do it in many ways, but two very simple equations can be used to that. So if you are dealing with a gray level image, you only consider, for instance, the gray levels of each pixels. In our case, you're not dealing with pixels, but you're dealing with superpixels. So all you have to do is take the mean value of each superpixel and establish a threshold. So if it's above this threshold, you simply say there is no connection between these two superpixels. Okay. If it's below that level, then you consider that weight as the link, the edge of superpixel I to superpixel J. Another parameter which we take in account to form the graph is how far should we go in computing weights from one superpixel to the other. So we establish a radius r, which gives you the range, yeah? How far we could go in linking one superpixel to the other. So in that way, we end up with a graph or a matrix of weights, which may have zero values if some pixels have no relation whatsoever with another pixel or superpixels, or respective weights as it should be. So this is the same for RGB images, so we apply in both images here, okay? Fine. Okay. Another key concept, and that has to do with the community detection algorithms, is how do you tell if this partitioning that you computed is good enough, yeah, as an image segmentation. But because in the end of the day, by grouping, by computing communities, you can say, well, if this is a community, then just label those pixels as belonging to a unique region in the image. Okay? So, and how do you tell that this has been a good computed partitioning? So, again, there are many estimates in the literature that tells you if the partitioning is good enough. Modularity is one of them, and what you do here is you given a certain amount of communities, which is, well, then it depends on the algorithm you're using, but let's say the algorithm figure out that it should partition your graph in 10 communities. So k is equal 10, so you compute a matrix k by k, which gives you in which each element, Eij, is a fraction of all edges in the network that link vertices from community I to community J. And although this is not in itself a very expensive procedure, you have to do that for every single partitioning. The algorithm, the community detector algorithm, does in the network, in the graph. So, if you have to compute k for all single setup of this partitioning, for all single community, then that's a very time-consuming process. And what the main community detector algorithms do, they actually run some optimization process to drop this processing time. So you don't go about trying to solve the NP-complete problem, but you just find some good approximations for that. Okay? Fine. For instance, one of the major algorithms available for community detectors that we found would be suitable for image processing or image segmentation is the fast greedy algorithm. It's quite simple. It's a greedy strategy which starts by labeling each graph or each pixel, right, each node in the graph as a unique community. Okay? Then it goes grouping 2 by 2. Yeah, it starts here, grouping 2 by 2 communities or nodes, and at each stage it computes the modularity, the key value. Okay, so it goes on doing this until the whole image or the whole graph becomes a single community, and the level for which modularity key is higher, then that's the best partition found. So then we end up with, in this case, with 2 communities, each one formed by 1, 2, 3, 4, 5, 6, and the other one by also 6 elements. That's just a simple example. Okay? Right, so how do we do that? So we start with the original image, and then we run the superpixel extraction, which is, as I'm going to show you, could be quite straightforward and not very time-consuming process. Then we generate the graph using one of those equations, the weight equations that I've shown you, and then we detect the communities. As simple as that. Fine. And some things here I already talked about, which are the, let's say, the superpixel computation. I would like to bring your attention to the parameters used and the parameters that have to be set up in order to run these experiments. So this is one of the major questions always in image segmentation. How parameter-free is your method? Yeah, that should be a thing that has always to be answered. And for the superpixel computation, you have to consider the size of the superpixel, obviously. Yeah. The number of iterations. Some of these things have already been sorted out. We've extending this work, and this has already been taken care of. The weights, I didn't mention that, but remember those 2. I'm going to go back here just a while. Here, okay, this is quite important. Lambda 1 and 2 actually tell how important or how much should I consider the region information? For instance, lambda 1. So if I say this is 1, so I'm saying that the region content is very important. And lambda 2 actually gives more importance to the convergence of the boundary itself. So by raising this value lambda 2, I'm saying that your superpixel, the boundary should be more rigid, so it shouldn't vary that much. That's what it means basically. Fine. Okay. So these are very important parameters, and a slight change in these parameters may change our segmentation quite considerably. And this is for the superpixel computation. The graph generation, there's nothing more to say about this, because I've talked about this equation already. So for gray level images, you can use this formula here to compute the weights. Fine. So obviously the edges are defined based on this mean intensity of the superpixels. Remember now that we're not dealing with pixels alone, but with a set of pixels. For colored images, we apply this formula here. All right. Just one thing about the parameters used in the graph generation step. Apart from the threshold, we have to provide a radius r, which, as I explained, is the range. Given a central point here, how far should I go towards the boundary, towards the outside of the image, and how far should I go in order to consider the neighboring pixels around the central pixel here, or central superpixel? Okay, this is quite important as well, and this is somehow by changing r, you can change the way the segmentation will come out. Fine. Okay. Experiment 1. So when we started dealing with these things, we said, well, what if we start with a superpixel size 10? What is the influence over the computation time if we vary the superpixel size? So this first experiment, it's in fact not to say if the segmentation is good or not, because the image is very simple and this is not the main goal here. So obviously it should perform 100% accuracy as it did. But how, by varying the superpixel size, how the computation time would come out. So that's obviously the result of the segmentation as it should be. But then we started analyzing how the changes with these parameters here. Yeah, so we 10 by 10, 15 by 15, up to 200 by 200. So what would be the behavior of the computation times given those parameters? So remember, why for larger superpixels the lambda 2 parameter is larger? Because then you allow the superpixel, the boundaries, to be more flexible, as it should. A larger superpixel, maybe if the object is smaller, you should allow the boundary to be more flexible. That's the idea. Okay, and this plot here shows, this is time in seconds. As you increase the number of superpixels, so this is somehow included here, the blue line. So the blue line is the superpixel time. As you increase the superpixel time, the superpixel size, the time convergency for the superpixel also increases, which is obvious. Yeah. So the trade-off then should be okay. So this is all the 3 times involved in the process, the time used to compute the superpixel, the time for to assemble the graph, and the time taken by the fast greedy algorithm. Okay. If the superpixel is too large, it takes longer to converge, so the time increases. And obviously, if you have a larger superpixels, you have less edges, less pixels in the mapped onto the graph. So obviously, the fast greedy would take longer. But then you have to find a trade-off here. So we found out, we showed that the proper thing to do is to use superpixels either 10 by 10 or 50 by 50. The largest value should be the thing to use. Okay. An experiment 2. Then we moved on to real images to show how changes in the parameters would affect segmentation. This is an image of a flower. This is the superpixel size 10 by 10, 20, 50. And this is the segmentation provided for 10 by 10 and 20 by 20 superpixel sizes, so which was the same. If increased to 50 by 50, so the segmentation isn't that good. And one thing that we experimented also is, so okay, so what about the parameters? We fixed 10 by 10 superpixel size and changed parameter, the network parameter, so the threshold which was used to compute whether I should link one superpixel to the other and to define the edge, the weight of the edge. And just by moving, by changing the threshold value, so we got a different segmentation. Is this good or bad? So I think this is has to do with the subjectiveness of any image segmentation process. It could be bad if you think that it doesn't matter if I segmented the inner parts of the flower, but it could be good if you consider that the flower actually has an inner part. So by changing the parameters, you can reveal some unexpected or segmented regions which you wouldn't have segmented if the parameters were otherwise. Again, this is for the computational times. You see, if the superpixel is too small, obviously you take more time to compute the complex network, to compute the community detector algorithm. If the superpixel increases, the time drops because the complex network is less complex, if you can say that. Okay, but again, this is something we would never achieve if you consider the pixel itself as opposed to superpixel strategy with any community detector algorithm. Yeah. Again, then just to show another experiment, these token images. It's a larger image, and here we compare our method with 2 other approaches we found in the literature. And again, it's to be fair, we decided to take some methods, obviously, that we could run in our computer, and not only to compare time found in papers, related papers. So we took these 2 methods here. This is a graph cut strategy combined with some hierarchical decomposition of the image. So it does it quite a few times in the image, considering different scales. And Fines-Walp method somehow more statistical method. Sorry, that is also graph-based, but it also takes into account how feasible a pixel should be related to the boundary of the image. So it's in fact it's more concerned with if the final segmented image would provide crispier edges or not. Yeah? So the results. Our method was slightly slower, faster than Weisenswald. This is the result we obtained. This is, in my opinion, not very important. The time processing, obviously, this is one of the good things about the method. But I believe that our method, I think, it's less prone to over-segmentation as opposed to Weisenswald method, although this is quite fast as well. And the problem with this method, although the technique itself is quite linear, it processes in quite linear computing time, it takes a lot of time to do the hierarchical process, and that's why it took a long time to process. Also, I don't think the edges here, as the boundaries here are so well defined as ours. These are some other experiments, just for the sake of showing how suitable it is for segmenting real images. Again, it's a non-supervised method. It does require the configuration of some parameters, but once you set up the parameter set, it does the job all alone. And as soon as we ran these experiments, we thought, so we have to tackle the parameter problem. This is something we have to deal with, and we are dealing with right now. We actually have already dealt with some of it, and it's working quite nicely now. The other thing is, what if you've provided some results on gray level and colored images? What about replacing and shifting these things to texture? And this is something we are looking at now, and it seems quite promising, I guess. We are trying to replace the color information or the pixel intensity information for texture. And also, we've just realized that RGB is not the best thing to do in relation with colored images. We are trying to replace the color model, which turned out to be much nicer, and in fact that's one of the reasons why we solved the parameter problem, some of them. And that's it. And here are some references, and these are the responsibles for the work. Thanks very much.
Any question?
I'm not sure I understand exactly what you're trying to do with your method. There are some. Here are some questions. First, you start from a superpixel or first segmentation. Weisenswald method is designed to do superpixel, not to obtain a full segmentation. So comparing the two is kind of well, you want to group superpixels, and your method is designed to do that, but not the one of Weisenswald and not the one of Weisenswald. And so the second question maybe is that you can start from any kind of superpixel. You propose some, but why not using a simple watershed, for example, that you can filter more or less to obtain more or less larger region? So well, these are two questions. What I want to understand exactly is what you're trying to do, and what is your goal, and why do you choose for this kind of superpixel rather than a simple watershed? what do you want to achieve
exactly. We believe that well, it all started with shall we try, or let us try segmenting images using community detector algorithms. Okay, so that's been done for many other applications. Yeah? Grouping, take some data and model it as a graph and apply community detectors algorithms for data clustering. So that's very much related to data clustering. Okay, let's do this data clustering for image segmentation. So, okay, model your images as a complex network. Take one of these. I mean complex network because the community detector algorithms, they apply some measures from the complex network field anyway, and try to see if you can achieve segmentation by doing this. So it wouldn't be possible because the size of the network and all the computation related to it, and it wouldn't fit the memory maybe sometimes. So you would need quite a good amount of memory to do that. And that's the reason why I decided to use a grouping strategy. It could be, as I said, watershed. Yeah, I don't see why. I mean, what we are trying to do now is we are, to be honest, we are not concerned very much with that now. So any grouping technique would do. Exactly. But what we are trying to do now is not only be a user of community detector algorithms, but to provide or to envisage or to come up with a new grouping algorithm. So we are trying to, what we've just come out with is, why not do some random walk or apply some Markovian strategy to group these pixels. Yeah, try to mix Markov random fields with and try to devise a new community detector algorithm. Because the algorithms, I didn't show it well, but another algorithm which is called label propagation, which is even faster than fast greedy. It does a very silly thing to group communities. So we could do that in a more images segmentation approach, appealing approach. Yeah. So that's what you're going to do. But any grouping technique would do, I guess. Watershed would do. I don't know. Well, there's an answer for that, actually. The superpixel is a quite nice means to converge, that allows the convergency of the superpixel boundary to the actual object boundary of the image. That was very convenient, and it was quite fast. I need no seeds to start the watershed.
You don't have any seeds. You don't have any seeds if you take a full watershed. You need seeds only if you want to find objects.
Okay.
But,
you're right.
And if you're using FenzelFab, for example, you don't have any seeds either, and you have very good superpixel.
Yeah, we could try that. And should be.
More questions? We have a short time to finish the session.
It's possible with your method to get some information about the morphology of segmented regions. For example, in astronomy we have a problem to detect the morphology of galaxies. For example, in large images, spiral galaxies or spherical galaxies and other types. Your method can help to solve this problem.
I didn't talk about the superpixel implementation. This ended up being a quite good thing to do because you have all the information about the superpixel, boundary pixels, internal pixels, and it could be straightforward to get some signatures from the superpixel itself. I mean, I'm not talking about the the object, but the object is a group of superpixels. So if you take the superpixel itself, it could be a straightforward thing to do is to get some signatures from, we have the boundary, so from the boundary we can extract many shape descriptors or shape information as regards with the shape and morphology of the object. We could do that somehow because it's all in the internal structure of the algorithm. That could be done. We didn't think about it.